Thank you, Jimmy, for giving me the floor to speak. In my today's talk, I would like to introduce one of our recent work that we presented in CVPA 2025 as a highlight. So it's actually one efficient AI. So how can we actually reduce the compute burden of existing architectures and come up with a very efficient solution? So it's called EffiDec3D, an optimized decoder for high performance and efficient 3D medical image segmentation. So it would be bit more technical than like others, I believe, because it's based on a paper. So we would like to introduce our like problem statement, and then I will go through our methodology. So let's start with the core application. So this is for 3D medical image segmentation. So what is 3D medical image segmentation? So 3D medical image segmentation, it deals with CT, MRI, ultrasound, or other medical imaging volumetric images, or even we can use those for like videos. So here is our goal is to identify the landmarks or biomarkers inside an image. So but it's segmentation, so pixel wise classification actually. So automatically labeling organs or lesions or tumors or other different structures of interest inside a volumetric CT, MRI, ultrasound. So here is I am showing an example of a CT frame that's extracted from a volume, and then in the second in the right image, so I am showing the overlay one of it. So that actually try to show the segmentation mask that's manually labeled, but our goal is to automatically label it using AI or deep learning algorithms. So why do we need this? This is actually a critical step in disease diagnosis and monitoring as well as surgical planning. So it can make the things faster. So one recent report shows that 82% reduction in image analysis time if we use AI in place when in the clinical workflow. Another thing is like it can also help in annual savings around 3.7 billion in US. Additionally, 28% of improvement in early disease detection. That's very important. So if we can detect disease early, that can help to reduce the death due to cancer and other different kind of disease. So let's start with what are the methods that we use for this kind of segmentation task for 3D segmentation. So some of the very popular methods are SwinUNETR, SwinUNETR version 2, 3D UXNet, and MedNext. Among these, SwinUNETR and SwinUNETR V2 are transformer based, and 3D UXNet and MedNext are CNN based. However, all of these methods, it has very high computation, high segmentation accuracy. However, it comes with very large compute and memory demands. So, and that actually requires high training and inference latency. Last year, I was in NIS, and I was working as a flow there, AI flow. However, what happened, like the lab I was collaborating with, they said that like we are using SwinUNETR always. However, we find it very tedious process to train a SwinUNETR network. It's require like huge amount of time. How can you actually optimize this kind of network? So that actually helps me to motivate in this domain to optimize this kind of existing network. So and that can help to actually reduce the like make our model like applicable to point of care devices, even low resource setting devices having limited to no GPU access. So this is even essential because nowadays point of care devices are very much common. Point of care ultrasound devices that we can use in bedside, point of care magnetic resonance images that can also be used in bedside. And if we can actually do the AI algorithm run on top of edge devices or point of devices, that can actually make the things faster, and we can do real-time analysis even on the bedside. So for this reason, there are some effort in place of a lightweight and efficient algorithm for segmentation, 3D segmentation. Some of those are SwinUNETR, UNETR++, SegFormat 3D. However, this method comes with low segmentation accuracy. So our goal is to how can we bring state-of-the-art high-performance segmentation networks in point-of-care devices. That means we have already a high performance networks like SwinUNETR, SwinUNETR version 2, 3D UXNet or Madness, or even like recent if something come with like very higher accuracy, we is there any way we can find out the bottlenecks there and optimize those network so without losing that much accuracy? So our goal is that, and in this work we try to actually address this issue and come up with a solution. So let's try to find out what are the bottlenecks of existing state of the art methods. So I will start with that. So here I consider the 3D UXNet. So one of the popular method that published in iClear 2023, and they come up with a CNN based network that uses connext kind of convolution blocks to process the image. It's encoder is very lightweight, only 1.31 million parameter, and flops is 7.81 for a volumetric scan of 96. However, the decoder, it comes with very high compute. So around 98% of the compute come from in the decoder. So which part of the decoder is actually responsible for this computational resources requirement or parameter and flops? So we try to identify that. So we have found that the main culprit for the flops is high resolution stages, which require around 60% of the flops of the whole decoder. So we propose a strategy that we can actually restrict the resolutions. So why we can restrict the resolutions? Because if we do processing on the high resolution stages, that's actually not giving us that much improvement in dice score. That we did sensitivity analysis and find out that without the high resolution stages, we have 79.4% dice score in one data set, and if we use those high resolution processing, we get 79.7%, just only 0.3% increase, but we have additional 60% flops. Additionally, in simpler data set, we have found that if we remove those high resolution stages, we can even get better dice score. So it can sometimes improve even reducing those kind of processing. So that's one thing. Another thing, we try to see what are the main bottleneck for number of parameters, high number of parameters. So we have found that the high number of parameters are due to a high number of or excessive number of channels in the decoder stages. So if you see here, so in case of bottleneck, it has 768 channels, and in case of the next stage, it has 384 channels. So that actually responsible for 87% of the parameters. So to optimize this part, we propose a channel reduction strategy, and our solution involves using a uniform channel all over the decoder. So this can be used in like even other architectures, not only this one. So we can actually use in any decoder heavy architectures this optimization. So based on these optimizations, we introduced EffiDec3D, our 3D optimized decoder that can be used as a plug and play for any U-shaped network. If decoder is heavy, we will get like more benefits from this optimization. So here is our optimized architecture. So if we see that our decoder has just only 43.66 gigaflops and only 1.84 million parameters, that's 93% reduction and 96.4% reduction respectively. And in case of channel reduction, we introduce a channel reduction block that uses a residual block actually. But in this case, we actually first reduce the number of channels from the encoder stages to a uniform number of channels. In our case, for this case, it's 48. We try to find it using the minimum number of channels across the stages. So these 48 channels we provide like all over the decoder, that helps to reduce the parameters significantly as well as flops. Additionally, as we said, like we would like to restrict resolution, so we restrict resolution to depth, height, and width by 2. So that actually helps to reduce the number of flops without affecting the accuracy that much. So let's have a look here. Here we have shown like the plot for different resolutions, compute requirements, parameter and flops. And if we see that, so if we see that in case of low resolution but bottleneck layer, so it had initially more than 24 million parameters, but our strategy optimized this model and reduced the parameter and flops to 97.6%, so it's just only 0.58 million, so it's significantly lightweight than the initial one, and that applies for all other stages as well. And in case of flops, if you see, as we do not have the high resolution processing on top of depth, height, and width, so we do not have such kind of parameter and flops requirements in those stages, so it reduces 100% flops there, so that was around 350 gigaflops. So this is significant savings, and we come up with a very lightweight network for 3D UXNet that has only 51.47 gigaflops and 3.15 million parameters only. So now I would like to show you some ablation studies to show how does this actually affect the performance, and also, sorry, also the number of parameter and flops. So our original model had 53 million parameters and 632.19 gigaflops, and if we apply the channel reduction only, so it reduced the number of parameters to 3.55 million, but still the flop requirement is 404 giga. So but reduction in dice score is just only 0.3%. This is a challenging task because we need to segment like different shape organs as well as like 14 different classes here. So in case of our high resolution restriction, if we actually restrict the resolution to just half resolution, so in that case our flop significantly reduced to like 51.47 giga. Even if someone would like to early exit, so do height, width, and depth by 4 for like S computing task or something, they doesn't care about accuracy that much but need faster processing, so we can do even like depth, height, and width by 4, but we need to actually sacrifice or lose more dice score in that case. And we have seen some cases that smaller organs are affecting more in those cases, as we do not have like fine grained processing of like depth, height, and width by half resolution and like full resolution processing. So in case of channel count in the decoder, so we first identify we would like to use uniform channels all over the decoder. But what would be the uniform channels? So we try to actually do a ablation here. So we have found that if we use a smaller number of channel all over the decoder, for example 16, so that actually reduce the dice score. But if we try to increase it, it increases sometimes but not always. So that we stick to the number of decoder channels equal to the minimum number of channel all over the encoder. So in our case it was 48, so we choose the 48 here. But if you like to have better dice score, you can use larger number of channels, but you need to actually incorporate more flops and parameters in that case. So here is another ablation just to show like how does our two component collaboratively optimize the architecture computes as well as also improves or also lose the performance. So our original decoder had 51.69 million parameter and 624.16 gigaflop, and it had dice score in BTCV 79.74 and in theta 87.28. So if we remove like this component, for example, do not use the channel reduction, just only use high resolution removal, or if we do not use like high resolution removal, it has like different effect. So in case of, as already we have like shown that if we use the channel reduction, it helps to reduce parameters significantly. For example, here 93.1% reduction. In case of high resolution removal, it has effect on the number of flops, significant effect. So in general, when we combine both of these together, our decoder has just only 1.84 million parameters, that's 96.4% reduction, and only 43.66 gigaflops, that's 93% reduction. And in case of small, like simpler task having 8 different classes, we got even improvement over the baseline. 87.28 was baseline, but we got 87.97, so it's like 0.69% improvement. But in case of a bit complex data sets, we got 0.5% reduction in dice score, but with significant savings in computation, parameter flops, and we'll show like even latency improvement in next slides. So here we compare only the decoders, but over multiple networks. So we consider SwinUNETR, SwinUNETR version 2, 3D and MadeNext. So in case of first three networks, so they have a common kind of decoding mechanism, having very heavy decoder, but come up with like high dice score, although, but it's not like the dice score improvement is not proportional to the increase in the compute. So we apply our strategy here, like optimization strategy, and we got like 95% around reduction in flops, but we lose only just 0.8% dice score maximum in one model like SwinUNETR version 2. In all other cases, we have significant savings with just only 0.34% reduction in dice score. So here is the results of BTCV 13 organ segmentation. So this is the average result or average dice score that we plotted here. So the red curve, it actually represents the number of flops, and the bars represent the dice score. So if we see that the like deep blue ones are our optimized methods, and before that the light ones and the original MadeNext and all the original methods. So if we see, this is actually the parameter and flops reduction for whole model, so including the encoder. Although we didn't actually optimize the encoder itself, just optimizing the decoder can actually reduce the MadeNext parameters 67%, 3D VxNets 94%, SwinUNETRs 84%, and SwinUNETR version 2 78%, because it has a comparatively larger encoder. And if we see, the dice score reduction is marginal, not that much in this complex dataset. So this is another dataset. So here we have 10 different tasks from the medical segmentation decathlon. So in this case, if we see, our model optimizes or reduce the computes, but it gets on an average better performance. So it improved the performance in all different models here. So 3D VxNet, SwinUNETR, and SwinUNETR version 2, but significantly lower computational requirement than the original model. So here we try to show the throughput. So how much like images per second our model can process. So this is actually not single image, this is volumetric scans. So in our case, we have found that this is for the forward pass, we averaged over 200 images, and if we see our 200 volumes, and if we see here our like original here it's bold, so our optimized models always can beat like the beat the original model in performance, but with higher throughput, so can process more volumes per second. So in case of higher throughput methods, SwinUNETR or Segperma3D, they have like very high throughput, but the thing is their dice score is marginal, so, and like very low, it's less than 64% on an average, where ours is more than 74%. Based on like different networks, is 72 to 74%. So here is a qualitative example, and we compare different methods here. So if we see that in the first example, most of the methods can actually segment. For example, the original method and our optimized methods has similar kind of quality outputs or segmentation outputs. I would like to just highlight one thing in the second image. So in this case, if you see the esophagus, so it's actually the pink region here, but if we see these methods, UNETR, NN former, and or NN UNETR plus plus, they cannot identify this or segment this class. And in case of 3D UXNet and MedNext, those are convolution based methods and doing like great in these cases. However, the thing is, these methods, our method, although optimized for computational efficiency, can also segment this part, so this esophagus region. But in case of SwinUNETR, the original one cannot actually segment, but our method can segment in this part as well. So these are the quality results. So we have more on our paper, so you can explore there. So now I would like to share the key takeaways from our paper and today's presentation. So we introduced EffiDec3D, a fast, lightweight, and accurate decoder. So, and it can be used with any U-shaped architectures, but it would be very good to use with decoder heavy networks. In that case, we can actually reduce the compute significantly. So we applied for 4 different architectures even in our paper: 3DXNet, SwinUNETR, SwinUNETR V2, and MedNext, and we have found that it's working great there with just marginal loss in dice score. So in case of parameter reduction, we got up to 17 times reduction in parameters. In case of flops, it's up to 12 times reduction. So, and inference time in GPU is up to 4.5 times, and in CPU is more, 8 times reduction. We evaluated on 13 tasks, so including BTCV 13 organ segmentation, BTCV 8 organ segmentation, fetal brain tumor segmentation, brain tissue segmentation, and 10 medical segmentation decathlon. And on an average in this 13 tasks, we got 1.33% improvement on dice score while using significantly lower computes. So we have seen that dice score increases in simple datasets, but marginal drops in complex multi-class datasets like BTCV. So in future, we would like to we already come up with a like new architectural design based on our optimization. So it actually uses two kind of optimization. So first we optimize the architecture using EffiDec3D kind of decoding. So channel reduction, as well as we could apply the resolution restriction, and then we can actually recap the segmentation performance using improved segment like processing blocks. So for example, maybe improved convolutional block or improved transformer blocks. Our paper is accepted at MICAI 2025. So in that case, we can also like get more improvement in dice score, but keeping the number of parameter and flops very low. And that can use for edge devices or point of care devices very easily. So another thing we would like to, or we try to come up with a ultra lightweight architecture design for specifically for edge devices. So that like our model is very lightweight, we can easily fit in the edge devices. This one is accepted in ICV 2025 CVMD computer like medical vision workshop there. And our next plan is to work on data efficient training for data scarce scenarios. So computational efficiency is one angle that we address this work, and in some of other follow-up works, but we'd like to consider the data efficiency angle. So use smaller number of data, but we'd like to get like even better performance or closer performance to using a very larger amount of data. Another thing that's I believe like also important, vision language model, those are sometimes come up with very high compute. So there is very less effort in that case. So we can consider that case to make it efficient. So we do not need to use the EffiDec3D type of optimization. There may be some other kind of optimization based on finding out their bottlenecks there. So um, Additionally, we can work on maybe efficient generative model. So current generative models like diffusion models, or sometime the generative adversarial network models, they come up with high computes. So we can try to address that limitations and come up with efficient models so that we can do those kind of stuffs very efficiently, even sometimes in edge devices if we need to be. So that's all from my end, and my email is here. You can email me for in case of any questions, or you can contact me in LinkedIn, and you will find more of my works in my website. You can scan the QR code, and we have our code publicly available of this EffiDec3D method that will find using or scanning the QR code here, as well as you will find the paper link there. And our group more or less work on computer vision, efficient AI, as well as medical vision. So you can explore our group's website as well to get more efficient AI methods, or like generative AI methods there. Thank you for listening. I will happy to answer any question.